Hey everybody, welcome back to number theory and our study and investigation of primes and composites. Just a little reminder of what we did at the end of last lecture. We said and we proved if P is prime and P divides the product of n factors, then P actually has to divide one of those factors. That's what we proved. So if a prime number divides a product, that prime number has to divide one of the factors of that product. Now, let's look at this. P is prime, and Q1, Q2, Qn are prime. If P divides the product of prime numbers, well, let's see. This thing tells us that P has to divide one of those primes, which means that this prime has to equal the product of two natural numbers. Well, this prime only has two factors, one in itself. So apparently, if P divides the product of primes, not only does P divide one of these factors, P is equal to one of these prime factors. And that leads us to the next theorem. It has a name, so it must be pretty important, even though the word arithmetic appears in the name of the theorem. So every natural number greater than 1 can be written as the product of primes. And that product is unique as long as we're disregarding the order of the factors. Whoops. Excuse me, I can't use n for two different things. So we'll say it's the product of r different primes and P1 is the smallest of those primes, P2 is the next smallest, and so forth. This is called the canonical or undisputed representation as the product of primes. And what would be a good example? Let's say 108. (108) divided by 4 is 27, and that is 3 cubed. Let's see if this is right. Son of a gun. Yeah, 5 cubed is 125, and 8 times 125 is 1,000. So in these two cases, n can be written as the product of primes, and this is how we would write it canonically. Now, this is going to be a short lecture again today, and I apologize for that. But I would like to show you something that it's something you can prove, and yet it's very profound at the same time. This proof goes back about 2,000 years. It's fairly simple, but extremely clever. Let's do it. Classic theorem from mathematics. There are infinitely many primes. We'll list the primes, and we'll list them in order from least to greatest. There are only finitely many primes. That's what we're assuming. And we've got them listed here. So what we do is we compute the product of these primes, and we add 1 to it. So by the fundamental theorem of arithmetic, P has a prime factor. So it's P sub I, where I is some number between 1 and n.
I'll be locking up at 3 o'clock.
I got you. Note also that P sub I divides this product, since P sub I is one of the prime number factors of this product. So P sub I divides P, and P sub I divides this product, which means that P sub I has to divide any linear combination of P and this product. So P sub I divides P minus this product But let's remind ourselves of what P, capital P is. Capital P is the product of all of these primes plus 1. That's what it is. So this whole thing, P minus this product, is just equal to 1. Now, we had a theorem about divisibility in the last section. And if an integer divides 1, that means that that integer is either equal to plus 1 or minus 1. Okay. Is it soup yet? What on earth? Let's see, where are we now? Let's think about what it was that we're doing. We're doing a proof, and we're doing the proof by contradiction. So has the you-know-what hit the fan yet? I think it has. Where's our contradiction? Do you see it? P sub I is a prime number, and here it says P sub I is either plus 1 or minus 1. Well, if P is prime, it's greater than 1. So P can't be negative 1. And if P is prime, since it's greater than 1, it can't be 1 either. 1 is neither a prime number nor a composite. Remember that? So if P is prime, the smallest that P sub I can be if P is prime, the smallest P sub I can be if P sub I is prime, there I got it right, is 2. If P sub I is prime, P sub I has to be at least equal to 2. So it can't be equal to plus or minus 1. There's our contradiction. You see, it's not that complicated, but it's a powerful result. There are infinitely many primes, and this proof is well within our grasp. Study it. Try to reproduce it without looking at the notes. If we get stuck, peek at the notes and practice doing it. This is definitely one of the classic theorems and the classic proofs of all time. It's not all that complicated, but it did require a stroke of genius. And that stroke of genius was the fact that whoever it was that did this, and I don't know if it was Pythagoras or Euclid, maybe Archimedes, one of those guys. I should know this. I'll tell you what, look it up in the book. They have the author of this proof. But the stroke of genius was just to take this number and add 1. And since we're assuming there are only finitely many primes, this thing has to be composite, especially since it's larger than the largest prime p sub n. See, this product is certainly larger than p sub n. So this cannot be a prime number. It's larger than the largest prime p sub n. And the stroke of genius was just coming up with this number to use to do a proof by contradiction. I hope you enjoyed that proof. I'll get back to you soon. In the meantime, stay safe, stay healthy. Don't worry about what we can't do, just worry about what we can do. And one of the things that we can do is study and learn these things. We can get a lot done in the remainder of this semester. And we're going to get a lot done in the remainder of this semester. Keep preparing. By the way, I have some solutions posted on my website. I sent an email out about that, but maybe you didn't see it. I have more solutions to the homework posted on the website. So investigate that. And definitely study today's notes, especially the fundamental theorem of arithmetic. Now, the theorem has a name, so that means it's important, even though it has the word arithmetic in it. Don't let the fact that the word arithmetic is part of the name lead you to thinking, oh, this isn't very important, it's arithmetic. The fundamental theorem of arithmetic is a classic theorem. Know it. This is a classic proof. Know that. If you're anything like I was when I was a math student, I felt a great sense of accomplishment when I was able to prove this theorem, and I think you will too. So study these notes carefully. Get familiar with the fundamental theorem of arithmetic. It's not complicated, but we should commit it to memory. And go over this theorem because it is a classic, and I know you'll enjoy mastering it. So stay safe and stay healthy.